Good afternoon, everyone. My name is Nilanjan Rao, and today I'll be talking about Speedo, fast dispatch and orchestration of serverless workflows. This work was undertaken by me and my guide, Professor Umesh Velu and Professor Purushottam Kulkarni at the Department of Computer Science and Engineering, IIT Bombay. So before I start talking about Speedo, let me talk a bit about serverless workflows. Serverless functions have been around for a long time. They provide flexibility and scalability at a very low level. However, they are limited by their functionality. Serverless workflows tend to overcome this limitation by allowing us to chain individual atomic functions into different architectures like 1:1, 1:m, or m:1, thus allowing us to overcome the limitation of functionality while at the same time allowing us scalability at a very granular level. However, fast systems of today are still encumbered by different limitations, one of them being the dispatch latency. Before I start talking about dispatch latency, let us see how a typical fast platform dispatches are triggered for a workflow or an individual function. When a function trigger comes in, it is queued up in the event queue. From there, it is forwarded to the orchestrator. The orchestrator decides if it is a single function request or if it is a workflow. If the function request is for our workflow, the orchestrator then steps in to orchestrate the workflow in different formats. However, if it's a single request, it is forwarded to the dispatcher. The dispatcher then decides if it needs to spin up a new resource or if it can directly forward the trigger to a worker. Now, the time it takes to move the trigger from the event queue to the worker is known as the dispatch latency. Let's now look into details into what contributes to this dispatch latency. On the right, you see a typical setup for a serverless system. When our trigger comes in, the request moves from the NIC on the server hosting the dispatch system and moves into the dispatch system running in the user space. The dispatch system then decides where to forward the request, and the request moves through the network stack again to the targeted worker. The worker then runs the request, executes it, and responds back with a response, which again travels back through the same network stack until it goes out of the system. Thus, you can see for a single trigger, there are about 6 network traverses involved, and this aggregates over and over again if we had considered cases of that of workflows. Now that we have seen how a typical dispatch system works and what are the components contributing to a dispatch system's latency, let us see what happens in real world cases. Let us consider the use case of Twitter. Twitter receives about 6,000 requests per second, which results in around 70,000 triggers internally. And they have a tight end-to-end turnaround time of around 10 milliseconds. Given these limitations, let's see how today's user space platforms like Knative or OpenWhisk or Xanadu perform. We send a request to empty functions to mimic such an environment. And as you can see, the dispatchers saturated at around 4,400 requests at max under load, which is nowhere close to the 70,000 requests per second that is required by applications of today. On the right, as you can see, even in the best case scenario of Knative, we get a mean latency of around 170 milliseconds and a 99th percentile latency of 2,700 milliseconds. Thus, today's single node dispatchers are unable to meet large scale application demands like that of Twitter and saturate at even very moderate loads and with very high dispatch latency. So what are we trying to solve today? We want to exploit networking hardware like SmartNICs, which provide in-network compute and programmability to minimize the latency that is incurred by modern day dispatch systems. So what is a SmartNIC? A SmartNIC is a packet forwarding device which consists of a packet gateway, a scheduler, and programmable RISC cores. At the same time, these smart NICs also contains a moderate amount of scratchpad memory, which can be used for general purpose computing. Thus, our target is to offload the fast dispatch system to take to exploit these hardware capabilities at the NIC to make decisions closer to the network. The key ideas of SPIDO is number one, network stack traversal is costly. So we need to take decisions closer to the network wire so that the latency can be minimized. And the solution to that is offloading the dispatch decision to the NIC. The second idea is that user space parallelism is costly and non-deterministic. So what do we do to solve that issue? We use ASIC-based scheduler that is available on the Smart NIC, and the RISC core or the compute cores available on Smart NICs as a replacement for the host cores. And finally, we have to remember that the dispatch system is not stateless and requires some state to be maintained. However, to our advantage, these states are ephemeral and short-lived or are very limited in size. And so the onboard memory that is available on today's Smart NICs are more than capable of handling such memory requirements. So now that we know how SPIDO works, let's see how SPIDO is architected. The SPIDO architecture consists of two parts. One that is running on the Smart NIC, consisting of a request parser, an orchestrator, and a dispatcher, along with some onboard memory states like the worker metadata and the workflow metadata. We also have a counterpart running on the user space with the dispatch system and the metadata and state. So how does SPIDO work? When a request comes in, the SPIDO orchestrator and the dispatcher on the Smart NIC takes a decision to decide if it's a cold start request or a warm start request. If it is a warm start request, the request is forwarded directly via the dispatcher to the worker node via the green fast path. While if it's a cold start request, the dispatcher takes a decision not to handle it itself and instead forwards it to the onboard host dispatch system and let the host decide where to spin up a new worker environment and also to forward the cold start when the worker environment comes up. This has two advantages. One, it minimizes the state requirement that has to be stored on the Smart NIC to a bare minimal. And two, it allows us to simplify the dispatch system or logic that is running on the Smart NIC. Now, let's see how the SPIDO dispatch system takes each and every part of the Smart NIC into consideration to dispatch requests. The first part is the scheduler. The scheduler that are available on Smart NICs are work conserving in nature and forwards triggers to any available compute cores. So this takes over as the event loop typically present on user space dispatches. Once a trigger is received at the compute cores, it requires some kind of state to decide where to forward it, or if it is a hot warm start request or a cold start request. This is done by using the function metadata available as part of the match action table on most P4-based Smart NICs. Once we have the state available, we run the dispatch and the orchestration logic on the RISC compute cores present on the Smart NICs. Each of these compute cores run in three stages. First is a packet parser, available as you can see in the bottom of the page. The packet parser now takes over as the SPIDO transport parser. Once the packet has been parsed, it is forwarded to the ingress control plane. The ingress control plane is a P4 logic that dispatch and load balance the request into different worker nodes. And once we have decided which worker node to forward the request to, the egress control plane works as a reverse proxy and forwards the request to the appropriate worker node. Now that we have seen how SPIDO works, let's evaluate SPIDO. We'll be evaluating SPIDO against Xanadu as a baseline, and we'll be asking two questions. What is the effect on the dispatch latency and throughput by this offloaded model? And how does SPIDO perform under real-world conditions? And we will be using these metrics of mean dispatch latency, the 99th percentile latency or the tail latency, and the dispatcher throughput. For our workloads, we'll be using two types of workloads. One for micro benchmark, where we will be running single empty functions and linear workflows. And the second one are that of macro benchmarks, where we will be looking into two different examples of social media write and movie review, which are inspired from Death Star Bench. Now, let's see how Speedo performs against user space dispatchers like Xanadu. We increase our load from 1 request per second to 1,000,000 requests per second and observe the throughput for each of the dispatches and also the tail and mean latency. At low loads, as you can see, Speedo has a dispatch latency of only 90 microseconds. As the load is increased and the user space dispatcher saturates, we can see that Speedo doesn't have any noticeable increase in its dispatch latency. And the mean latency stays 1100 times lower as compared to that of user space dispatches. And even at their respective saturation points, we can see that Speedo has a 500 times advantage over user space dispatcher like Xanadu. On the throughput scale, we see that Speedo outperforms Xanadu by orders of magnitude, being capable of dispatching up to 900,000 requests per second. Now, let's see what happens if we consider linear workflows. Even in this case, we see that the Speedo orchestrator doesn't increase the mean latency by a large amount, adding only 2% to the mean latency. And at saturation points, we can see that even then, the latency jumps from 900 microseconds to 9.2 milliseconds. And so Speedo improves throughput for linear workflows by about 500 times to 600 times on an average, and mean latency by 100 times. Now, let's look into what happens in case of generalized workflows. For this, we'll take into consideration two of Death Star Bench's macro benchmark. One is social media write, and two is movie review. In case of social media write, we can see that Speedo outperforms Xanadu by 150 times and has a throughput which is 2 orders of magnitude larger. We see similar cases for movie review also, where the Speedo dispatch system takes only 5 milliseconds and provides a throughput of around 80K requests per second. Thus, the Speedo dispatch system is capable of handling requests at scale. In summary, Speedo exploited compute and programmability of SmartNICs to improve fast management and provide orders of magnitude scalability, both in terms of throughput and average latency. As part of our future work, we plan to extend Speedo by allowing dynamic offloading of the dispatch system from the host CPU and the SmartNIC based on different conditions, like system of resources available at the SmartNIC and at the host. We are also looking into resource partitioning of our applications for multiple, where SmartNIC is shared amongst multiple applications. That's it. Thank you. For more details, please look into our paper.